can you please find your little notes from yesterday? We're just gonna finish them up. We had done like the first page. And we talked about the rational root theorem. If we have a polynomial, how can we figure out what the possible roots are, and then how do we check them? We'll do another one of those today. We talked about the conjugate root theorem. If we have a square root or if we have an I as a root, then its conjugate is automatically a root as well, aka just like its opposite sign is automatically a root. And today we're talking about Descartes' rule of signs. So I'm just going to kind of read through it. And then once again, when you read through it, it's always like gibberish. And then we'll actually do the math output behind it. So it says a method that you can tell how many roots to expect in a polynomial. Okay, so that's good. Just by looking at signs, we'll be able to tell how many roots to expect. It will not tell you where the roots occur. So it's not going to tell us like the root is at this point. It will just tell us how many. Just the types that are possible. This is helpful when you do not have a graph because you can't really tell. So there we go. So Descartes' rule of signs. The number of positive real roots of the polynomial's real coefficients is the same as the number of sign changes. Okay, so we're just looking, are things going from positive to negative, negative to positive, so when things are changing signs. Or less than that number, minus 2. We'll kind of get into that in a second. So I'm going to look at the example number 6 right there. And with that example, we're given a polynomial. Oh gosh, okay. So literally this is what you do. It's called the rule of signs because we're only looking at the signs positives, negative. Go through your terms and see if they're positive or negative. This is positive. This is negative. This is positive. This is negative. This is positive. So I literally just go through and see the signs. I don't actually even care about the numbers. People at home, let's see how dark it is if I turn the light off. I have such a glare with the lights. So can you guys function like this? Just at home with the light. Now we are looking for sign changes. So if it went from positive to positive, I don't care about it. I'm only looking for when the sign changes. So we have one right here where it goes from positive to negative. And then it goes from negative to positive, so that's another one. And then it goes from positive to negative, that's another one. And then it goes from negative to positive, that's another one. So that's not always going to happen that it always flip-flops. But in this case, it does. So what we say is we have 4 sign changes. So what that means, I'm just seeing my spacing over here. You guys have that little like chart. I'll just do mine quick. Just so we're on the same page here. What is it? Just making sure I'm still on the camera. All right, so we have positive real roots. And that's what we're talking about because we talked about P of X. We're going to do P of negative X in a second. So if there's 4 sign changes, that means there can either be 4 positive real roots, right? The same number. So if it's 4, it's 4. Or what the rule says, less than the number of sign changes by a positive even integer, aka you just subtract 2, okay? So there can be 4 or 2 or 0. Excuse me. So it's always how many sign changes you have. That's the maximum positive real roots since it's a thing. Or you can subtract 2 until you get down to 0, obviously. And that's how many possible positive real roots you have. Now we want to know how many negative real roots we have. So that's our next kind of column here. So to do the negative real roots, you're going to do P of negative X. This one, it's not long. You don't have to put too much thought, but you do have to think a little bit. So just think about replacing X with negative X. You would have negative X to the 4th minus 5 times negative x to the third plus 7 times negative x minus 5 times negative x plus 6. Okay, a bunch of stuff. You really just have to kind of think about, well, if I raise a negative to the fourth, or if I raise a negative to the third, is that going to be positive or negative? I don't really care about like the actual numbers, I'm going to be honest. I really care about what's the sign going to be. If I have a negative, negative x, and I raise it to the fourth power, will it be positive or negative? Positive. It'll be positive, right? Because negative times negative times a negative times a negative would be a positive. Okay, so this would be a plus. If I have a negative raised to the third power, would it be positive or negative? It would be a negative times a negative times a negative would be negative, right? Because 2 negatives make a positive. But then we have a negative here as well, so that's also plus. So a negative to the third is negative, but since I had a negative, it turns it positive. Should this have a squared? It should. If I have a negative squared, a negative times a negative is positive, stays positive, okay? I have a negative here, and there's a negative out in front, so that's positive. And then the last thing is also positive. Magical. So if I'm looking for sign changes, there are none, right? So the sign change is when it changes from positive to negative or vice versa. So we say there are 0 sign changes. And if there's 0 sign changes, that means there's 0 negative real roots. So actually, this whole column is all zeros. Just kind of seeing. So no sign changes means no negative real roots. And then the last column asks how many imaginary roots are there. You don't do that with the Descartes' rule of signs. That's just kind of thinking. This is a quartic, aka 4th degree. That means there's 4 roots. So if I have 4 positive roots, that means there's no negative roots and there's also no imaginary roots, right? Because the 4 roots are taken care of there. If I have 2 positive real roots with no negative roots, that means 2 of the other ones would have to be imaginary. And if I have none and none, that means in this case, I would have 4 imaginary roots. And that's just kind of going back to saying if something's a 4th degree, there's 4 roots. And if something's not positive or negative, that means it has to be imaginary. Yeah.
So the first one in the box was 0 because the 4 was taken care of by the positive, and then
exactly. So basically, I just want the sum of each of these to be 4.
Oh yeah, okay.
So I want the sum of them to be 4 since it's a 4th degree. That means that it has to have 4 roots. So yeah, in this case, the 4 were taken care of with the positive, or you could have that case where you have 2 with the 2 imaginary.
And just to make sure I have it right, as many sign changes is then this number of either the positive or the negative. But then when you said -2, is that for
yes.
Even if you get 9 or something?
So yes. So if you got 9, it would be 9, 7, 5, 3, 1.
Oh, well.
I mean, you can't go to you can't go to 0 because anyone can make it. So yep.
Okay, thank you.
So you're probably thinking why would you need this? I mean, it all just goes back to why not? We have all this stuff. It kind of just is a nice way to check that you're doing things correctly. So on this next one, we're going to try to kind of put everything together. We're going to be given a polynomial. We're going to do the rational root theorem. So where we do our lists and say what are the possible rational roots. And then we'll check how many roots should we have, and we'll use Descartes' rule of signs because that will give us a better idea of what we're looking for. And then what else we got? Oh, then we'll actually find the roots. Exciting stuff. So this is our last problem. It's on the very back. And we're going to do that, and then we'll kind of integrate this in as we do it. So once again, you're really just talking about signs, which is nice because you don't have to do too much extra. It's just knowing what to look for when you're looking up for signs. But let's kind of go back and do our last example here. I want to talk about the conjugate rule after. So it says find all rational roots. So before we find them, let's just do Descartes' rule of signs so we know like what are our options. So somewhere, whatever in your box. Let's do P of X. And I'm just gonna do my signs, pluses or minuses. So I'm starting with a positive, a negative, a positive. So from here to here, there's one sign change, right? From here to here, they're the same, so I don't do anything. And then from here to here, there's one sign change. That means we have two, I'll do P of net, I'm just setting myself up so I have some room here. So for positive real root, that's a positive real roots. Sorry, I'm just trying to write it the way I wrote it. Yes, positive real zeros. There's either 2 or 0. Those are my options. So it's something I want to keep in mind. Because remember, if we do this and then it told us they're all negative roots, we wouldn't even check the positives. So sometimes it will save you time, especially when you have to check all that list. If you realize, hey, like all my roots are negative, don't even check the positives. For negative, so I'm just going to kind of do this in my head. If I have a negative cubed, that's a negative. If I have a negative squared, that's a positive, but there's a minus in front of it, so that would also be a negative. If I just throw in a negative here, I have a negative as well, so that would be a positive, and then the last one's positive. So there's just one sign change. So for the negative real roots, or negative real zeros, there's one of them. Okay, so that's it. That's the only option. The option is there's one. So you can put one. If you want to put one with both, go for it. And then technically, since this is cubic, for imaginary, if I could write imaginary, there's either 0 in this case, right? Because if you have 2 and 1, there would be 0. Or if it's that case, we have 2. So we've at least narrowed it down a little bit. I'm gonna stick with, I know there's 2 positive real root, or okay, I guess there could be 0 as well, but I'm gonna stick with the positive ones. And I'll kind of check those as I go. But once again, that might be useful. Like, hey, I'm doing this and I can see that there's this many negatives or positives. And that gives me at least a heads up. So now as we do the rational root theorem, I'm going to do a little list, or 2 little lists. One of my constant. What are the factors of my constants? I have 12. I like when they're nice small numbers, but we can't make them all easy. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Okay. And then I do coefficient, the leading coefficient. Oh, that one's at least a little better. Plus or minus 1, plus or minus 2. And then I say, well, what are my actual possible rational roots? That's when you do constant over coefficient. So my options, if I divided each of these by 1, I would just get that list again. So I usually just kind of start by rewriting that list. Because if I divide each of those by 1, I'll just get the same old thing. And then if I divide each of them by 2, I would get 1/2. What else will I get? 2 over 2 is 1, so that's all set. 3 over 2. 4 over 2 is good, 6 over 2 is good, 12 over 2 is good. Okay, so those are my possible rational roots. So this is where Macalky comes in, because I don't want to do the next part in my head. I just start to go through and kind of check, because I have no clue what actual rational root works. So I go back to my original, and I start to plug stuff in. So I usually just go in order. Let's be honest. If not, you're just going to go crazy. So let's try P of 1. And once again, when I say P of 1, I can plug 1 in for X. and I'm looking to see if the remainder is 0. I will try to never give you one. Isn't it the worst if like you did all this and it was like this one? It's like, oh, that's the first one. So I'll try to be decent to you, just out of, these can get a little bit annoying. I'm with you. So I'll try to save you some time, or at least save you some sanity. Oh, that comes out to 3. All right, that's out. I'm gonna try P of 2. I always just go through and do the positive ones. So let's see if I take that and do 2. Ooh, and then you feel like so happy. Ooh, 0. That means 2 is a factor, or is a root, whatever you want to call it. So now we can do synthetic division. Our favorites. We can divide by 2. And we have the coefficients 2, -3, -8, and 12. Cha-cha. And this is why I like synthetic division, because it is so quick. And then I have a nice trinomial that I can factor. That's gonna factor 2. What would that be? 2, that would be 3, because that would be, 4 and 3. I want it to be +4, -3. And in the end, it asks, what are the rational roots? And you would say the roots are, don't forget about the 2, right? That's the first one that we found. Don't forget about it. 3/2 and -2. Oh my goodness gracious, what a long problem. Now, when we eventually have like a little quizaroo or testaroo, whatever, we're not gonna have you do 10 of those. They're annoying. So maybe there's one I just ask you for the Descartes rule of signs. Maybe I'll ask you about like how many zeros or how many possible zeros. Maybe there's one I just say, what are the possible rational roots? You don't actually have to check them. You just like do your list. Obviously there will be 1 or 2, maybe 1 or 2, where you actually have to find them, but just as a heads up.
Since it says that like 3/2 is a root, if you had plugged in like from the possible rational roots like 3/2, would that have like worked? You would have gotten 0.
Yep.
And then you could have worked that way.
Yeah.
Okay.
Hey, and guys, look at, there's 2 positive roots and there's 1 negative root. Oh my gosh, it's like this is magical. I'm just new. So you don't necessarily have to do that. You don't really have to do the rule of signs unless it asks you to. But for that one, I kind of just added it in, because we had just talked about it and just did a quick problem, and then it kind of relates it to our actual root. So basically, it told us we had 2 options, and we had the option where we had 2 positive real roots and 1 negative real root. And that was so fun. Woo! Okay. Oh my goodness gracious, we were chatting at the beginning, so now I'm all thrown up. I do want to do one thing, and the one thing I wanted to do with you is find the problem set that you guys were going to pass in today, and do that one last problem, guys. That number 80, let's just get it done. And I saved it because it has to do with the conjugate theorem, and we hadn't talked about it before yesterday. So if we were doing it, it would have made 0 sense, but now hopefully it will make a little more sense as we get into it. So I'm gonna read it and then I'll throw it up on the board. I'm just giving people another minute if they needed to copy anything. It says, if 4i is a root of, and it gives us a nice little polynomial, then find all of the other roots. So we already know 1 other root, because by the conjugate theorem, if I see an imaginary root, that means its conjugate is also a root. So I'll kind of show you the work and you'll see what happens. So once again, if 4i is a root, then I automatically know -4i is a root as well. So I'm just going to throw that out there. We are going to have to do some division though. So I'm going to take The original polynomial, I'll take the coefficients 1, 3, a 15, a 48, and a 16. And I'm going to divide it by 4i. And you're probably going to say, oh, that's not going to be beautiful. And you're right, it's not going to be beautiful, but it'll work out in the end. Okay? And you'll see why the conjugate's important in a second. So we just start doing our thing, and we say, oh, bring the 1 down. 4i times 1 is 4i. Like, what do I do? You literally, when you add these, you're just going to write this as 3 plus 4i. Okay. So you can't combine real and imaginary. Yes?
Where is this again?
This is number 80 in your problem set. Sorry, it was like the one that we hadn't done. Because once again, if you have a real and imaginary, you just kind of keep them separate. You leave it as 3 plus 4i. So now we're like, all right, we got to kind of keep going. So now I have to multiply 4i times this. That's fine. It's just a binomial, right? So 4i times 3 is 12i. And I'm also going to do 4i times 4i. What would that give us? 16i squared, which we're going to write as negative 16. I'm going to write it as negative 16 plus 12i. I just like to keep things in that order. It doesn't matter if you write it as 12i minus 16. I always like to put real and imaginary, just out of habit. Now when we combine, I can combine these real parts. 15 plus negative 16 is negative 1, and then plus 12i. All right, let's see what we got for the next part. 4i times negative 1 is negative 4i. 4i times 12i is 48i squared, which is really just negative 48. So I'm going to write it as negative 48 minus 4i. Okay. It's not terrible. It's just like adds one more thing to do. 48 minus 48. Well, that cancels, right? And I just end up with minus 4i. Because 4i times negative 4i is negative 16i. Wait. Did I mess up a sign?
No.
4i times 4i is negative 16.
It's 16 in the problem.
The 16?
Oh, that's
Top is
why.
negative.
I knew I did something. Okay, that makes more sense. I knew something went wrong somewhere. Because this is 16, so that's 0. Because that has to be 0 because we said that that was a factor. So you're probably saying, so what's my answer? I don't have an answer yet, right? Because I have one more step. And my one more step is, since 4i was a factor and I divided it out, I get this kind of grossness. But I also know that negative 4i is a factor. So what I'm going to do is I'm going to take negative 4i and I'm going to divide it by this answer. And you're going to see the magic that is about to happen. I don't need the 0, right? Ready? This is why you need the conjugate, because if you just divide that out, that's a big hot mess. Bring this down. I get 1. Zigger zagger. I get negative 4i. Magical. I'm just left with 3. Negative 4i times 3 is negative 12i. Magical again. I'm left with negative 1. Negative 4i times negative 4 is positive 4i. And what do you know? You get 0, which makes sense because this is a factor. And then we're finally down to like having actual normal numbers here. Just as a reminder, I can't even remember what we started with. This one, we started with x to the 4th. So when you divide that one factor out, that's x to the 3rd. So when we get to here, that's x squared. And when it says find other roots, we're actually going to factor that and actually find the roots. So I'm going to take x squared plus 3x minus, wait, I can't factor that. Oh, stank, I have to do the quadratic formula. Okay. Negative b plus or minus the square root of,
B squared.
wait, well, I know what it is. I forgot it. No.
I know, you're a math teacher, you should.
That's one thing that's like burned into my brain. I was just getting my calculator. B squared minus 4 times a times c, even though I probably could have done that in my head, gives me 13 all over 2a. Okay. So reminder, this was originally a 4th degree polynomial. This represents 2 of my roots. And then I also have the roots plus or minus 4i, or you can write positive 4i, negative 4i. So do we have 4 roots, Hex? Yes, we do. Plus or minus represents 2 here, plus or minus represents 2 here. But it was imperative that you knew, which we didn't know before, that if I see 4i as a factor, then I also need to know that negative 4i is a factor, and that comes from the conjugate theorem. And you can see if you just divide out 4i, that's not even helpful. This doesn't help us do anything. But once you divide out its conjugate, it gives you a nice polynomial that you can then find the root for. So that finishes that up. If you already scanned it or did whatever, you can, that's fine. Because I knew I had to finish that one with you. I'm gonna be honest, I thought I had the answer key and now I can't find it, so I have to finish my answer key. So I'll put that up in the next day or two. We can check over those, see if there's any questions. Yes, ma'am?
Can we go over number 81?
Yeah, we'll do. We might go over tomorrow, just because, I'm gonna be honest, I just don't have. Oh, yeah. We'll go over that one tomorrow.
Okay, so if we just scan it in
That's
without,
fine. Yeah.
what we're done?
You are good.
Wait, so we don't have to, like, try and understand number 81, or?
Huh?
Wait, so still attempt 81 or no?
It doesn't matter. If you don't attempt it, I won't hold it against you, because I will tell you we will do it later. Okay, so that one I definitely want to go over because we hadn't really talked about the conjugate theorem and I thought I might confuse you if I just threw it at you. But now we've seen it and we're saying, okay, that's not too terrible. I mean, once again, I like the conjugate theorem because it's really just knowing, oh, if I see a square root or if I see an I, you just have to do the conjugate just means the opposite sign. It's also a root. Sorry, I'm just trying to find my new problem set. Let me try to find it. Excuse me. Alrighty, my friends. I'm just gonna take this